phi e equal to 1 q is constant. Here it's at the center. 1 over 4 pi epsilon naught is constant. So I can write q over 4 pi epsilon naught an integral on a surface. And this is equal to sine of theta, d theta and d phi. And we know about this thing, that this thing is basically the solid angle in which theta is running from 0 to pi and pi is running from 0 to 2 pi, and this whole thing is equal to 4 pi. This is solid angle. So for this I can write that phi e is equal to q over 4 pi epsilon naught, and here this thing goes to 4 pi, and 4 pi will cancel with 4 pi, and we are left with q over epsilon naught. And this is the flux that we are having. This is the flux that we are having from this source charge q. Now if instead of one charge, if we will be having many charges, then when one charge, it will have electric field equal to E1, and when there will be another charge, we will have electric field equal E2, and for a third charge this will be equal to E3, and so on. As many charges as we have, we will have this thing equal to this. And I can write that this is for any number of charge. I runs from 1 up to n charges, we will have the total electric field equals EI. Now in that situation, we will have the integral, and the integral will be, then consider here that this is EI. So EI will replace this Q by QI because we will be having many charges, and then we will write it like this, that integral. Now if there will be many charges, then whether the sphere that we are considering is enclosing the whole charges, and this will cause this surface integral to be a closed surface integral, because it shouldn't leave the contribution of any charge, and we will write that this is E dot dA, and this is equal to summation on I running from 1 up to n, and then integral on a closed surface, and this is EI dot dA, and this thing is equal, we close the parenthesis, and this is equal to summation on I running from 1 up to n, and this is equal to this q will be replaced by qi and divide by epsilon naught. And I can then write from here that this is E dot dA on a closed surface, E dot dA, this is equal to the total charges enclosed here, and I write this is Q, capital Q, and I write enclosed, or I can write inside the sphere the charges, and over epsilon naught. And this thing we call is Gauss's law, that the flux is equal to Q, the total charge enclosed, by epsilon naught. Now here something exceptional is occurring, and this is we call is Gauss's law. Now Gauss's law is not Coulomb law, but if we add to Coulomb's law the superposition principle as well, then we will have Gauss's law. Now what this law is telling us, if we look here, this is not, the flux is not depending whatever surface you are considering, but it should be a closed surface. It should be a closed surface, then it is fine. Whether you consider a cube around it, and that cube, then the calculation will be different, but the result will be the same. And why here we just get rid of this thing? This is due to the Coulomb's law over R square situation. And we see here that R square cancels with R square. The electric field here is decreasing as 1 over R square, while the area element, it is increasing as R square, and both actually cancel the effect of each other, and we have the shape dependence here is null. The shape dependence is gone. Only a closed surface is required. And that's the reason, if there would be something like they would not be cancelling each other, then the shape of the sphere that we are considering, the shape of the sphere, or for example any other shape like cubic or ellipsoid, whatever we consider, then that would depend on the calculation, means that would have another value of flux. So this thing, this symmetry actually get rid of the shape, whatever we are considering there, the result will be the same. So if we will be having, for example, a spherical charge distribution, then we consider a concentric sphere over it, and if we will be having line charge density, then around that line we will consider a coaxial cylinder. And even if we will be having a cylinder, then we will consider a coaxial cylinder either inside or outside of that geometry. And in case we will be having plane geometry or sheet geometry, then we will consider a pillbox on it, such that half of it will be above it and half of it will be below it. It will be crossing through the surface. Now the final result we call is the Gauss's law. This is the integral form of the Gauss's law. We can convert this integral form into differential form by using the divergence theorem. And as I hope you would remember, that we have written the divergence theorem is, if we are having a volume integral and the divergence of a physical quantity, which is V here, and d tau and the whole volume integrated over the whole volume is equal to a closed surface integral, and this is the same vector you take on a surface, like the flux of that vector on the surface. Here you take the divergence, this last state, the divergence in a whole volume, like this is the divergence of this in the whole volume. This thing is the same if we consider the line itself. We consider the vector or the quantity itself and make its dot product with the area element we call is the flux. So by looking to this one, if I look to this side in here, then this is V dot dA, and this is equal to E dot dA. So replacing here the V by E, then I can write this form is integral on a closed surface and E dot dA, this is can be written is like this, integral on a whole volume, and then this is divergence of, for V I will write E and whole volume d tau, the friction volume here, which is to be integrated over, and this is equal to Q enclosed by epsilon naught. Now I know that Q enclosed is equal, this is the total charge, and if we talk in terms of the volume element, then the total charge will be equal to the volume charge density multiplied by the volume. So this will give us the total enclosed charge, and I can write for the Q enclosed this one, then this implies that a volume integral divergence of E is in d tau is equal to integral on a volume, because this is also a volume integral, and rho d tau here, and this will be divided on epsilon naught. So 1 over epsilon naught and rho d tau. Now if I look here, the divergence of E is just a number, and this is independent of the integration because it is independent of the shape we are considering, whether we consider a small sphere or a big sphere, or we consider a cube of any other shape, then it means that we have no integration on the divergence of E here, and then d tau here and volume here, while the charge density is constant. There is no integration on this one. So rho over epsilon naught, and here we will have volume integral and d tau. Now as both are the same volume, because this is the volume which is on which we are calculating the divergence, and this is the volume which is enclosing the whole charge. So it means whatever the result of this side is the result of this side, and they are cancelled with each other, and we get the divergence of E equals to rho over epsilon naught, and this we call is the differential form of Gauss's law. We also term this one is the Maxwell first equation. So the divergence of electric field is equal to rho over epsilon naught. This is the same law as here. We are having this in integral form, and here we are having this in differential form. Now this law states in differential form. This is very easy to understand. Look here, we are having divergence of E. How much this electric field is diverging? It depends only on two parameters. How much charge is there which is causing the divergence, and in what medium we have that, because if the charge will be less, the divergence will be less, and if we will have such a medium in which the permittivity of free space will be different, because this is the permittivity of free space of vacuum, and any permittivity which will be greater than this one will cause this divergence to reduce. So it depends on two parameters. What's the volume charge density of the charge, and in what kind of medium that is the geometry is placed, and like what is the geometry over there, and this will give us the divergence of electric field. So this is the differential form of Gauss's law, and we will term that one later on as the first equation of Maxwell. In section 2.2.3, we will now discuss the applications of Gauss's law, and we will solve some examples. These examples are based on three possible geometries. The very first one geometry that we will discuss will be a spherical geometry, and then we will discuss in another example the cylindrical geometry, and finally we will discuss the sheet geometry or the plane geometry or two-dimensional geometry. So first we will solve example 2.2, and in example 2.2, let me recite the example. It says, you are seeing it on the screen as well. Find the field outside a uniformly charged solid sphere of radius r and a total charge q. So we are going to find out the electric field outside a uniformly charged solid sphere. Solid sphere means that it is felt from the inside and all the material of this is charged. So we are having the geometry. Let me draw the geometry first. And the geometry is such that we are having a solid sphere. This is a solid sphere, and this sphere, in order to make it solid, then let me do like this. So this shows a solid sphere, and this sphere is having its radius equal to r, capital R here, and we are supposed to find out the electric field at a distance small r from here, like at this much distance, and this is r distance away from it, and this distance is basically this one at r distance. Now, as this is a spherical geometry, so around this spherical geometry we will consider another concentric sphere. So the concentric sphere is exactly the spherical shape here, and it is having a radius. Its radius is r, small r here. And now we will apply Gauss's law to find out this thing. We know about Gauss's law. This is our observation point P here. We know about Gauss's law that it is integration on a closed surface, and E dot dA is equal to Q enclosed over epsilon naught. Now here we know that the total charge this solid sphere is having is Q. So we will find the electric field outside the sphere. First we calculate this side, and this side is equal to integral on a closed surface, and this is E dot dA. Now as we know that it's a dot product here, and it will be equal to EdA cos theta, and as we have considered a concentric sphere here, and a concentric sphere, the E and the dA will be having because the line going from here, and I consider any pitch element or area element on the surface of this sphere, this will be radially outward. The direction of this one is radially outward, and the direction of the electric field will also be radially outward. So theta will be equal to 0, which will make cos 0 equal to 1, and E dot dA will become EdA, and it is here. that on a closed surface, and this is EDA, and this is equal to the enclosed charge. What is the enclosed charge? How much charge this sphere, the Gaussian sphere, is enclosing, and that is equal to Q. So the enclosed charge is equal to Q over epsilon naught. Now if I consider this E here, then on this side E is directed this way, but here it is directed this way and this way and this way. So in all three dimensions E is radially outward. It means that its direction on the surface is the same. So if I write here like this, that it is an absolute value here, EDA, then this is constant on the surface, because we know that electric field is equal to 1 over 4 pi epsilon naught Q over R square in our unit vector direction. Now on each point along this sphere, we are having it radially outward. We are having its dependence, or its value on the surface is R is constant on this surface. So electric field is the same. That's why it will go out of the integral.